Section 5.3 General Linear System. So here we shall be discussing solving an equation of this form where B may or may not be the zero vector. The first theorem in this section is that these statements are equivalent. Now out of these, the equivalence of first two is of great importance, and it is basically just like a restatement. One is a restatement of the other. We have already discussed this. Ax equal to b basically means that b is a linear combination of columns of x with coefficients taken from components of x. So if this holds, b is in column space column space of A. And on the other hand, if b is in column space of A, then you can express B as a linear combination of columns of A. For example, suppose I find that B is 2 times the first column of A plus 3 times the second column of A and minus the third column of A. Suppose this is my B. Suppose I have this, so this is B, this is the first column of A, second column of A and third column of A. In that case, I can collect all these things in this way, write them side by side. So I have the 3 columns of A written side by side, which means it is actually the matrix A itself. Then write 2 here, 3 here and minus 1 here. That is going to play the role of X. So B is equal to A times this 2, 3 minus 1 vector. So these two are equivalent. Now the last one is a very typical thing for Rao Bhim, putting some unnecessary condition which looks very complicated. What does this say? That A colon B, this means you have your matrix A and after that you also put your vector B. You make a bigger matrix with one extra column. Now if this is already a linear combination of columns here, naturally by adding this vector the column space does not increase because you are adding something which is already in the column space. So the rank does not change. And if on the other hand you are adding a new vector, that is you are appending a new vector and still the rank does not change, so the dimension does not change, that means that this must be already in the span of the first few vectors. Just for example, if I give you only one vector and with it I give you yet another vector and you find that the dimension of the span does not increase, that means that the new vector must be along the same line. Had the new vector been slightly off that line, in that case this will bring a fresh contribution. As a result, these two together will span a bigger space R2 in this example. So all these three are equivalent, but remember that these two, equivalence of these two is little more than notation. This is written in terms of vectors and this is written in terms of matrices. This equivalence is just an unnecessary appendage. This is called the augmented matrix of the system. So here is an example. Suppose this is our system. Then I take the coefficient matrix 2, 3, 5, minus 1 and after that append as a column 6, 7 here. So this is the augmented matrix of the system. In many cases we like to put a vertical bar as a separator. Of course, that remains the same matrix, just to remind ourselves that this is the right hand side and this is the coefficient matrix. Theorem 5.3.2 is one very typical Rao Bhim theorem, absolute rubbish, but just makes things complicated. So it says Ax equal to b is consistent if and only if for all u, whenever a prime u is 0, b prime u is 0. I have appended this for all u part. This was not given in the theorem, but you need that. Now, the first thing that I have to say is that forget about this theorem. This is not going to help you in understanding linear algebra. It is just a pompous way of saying a trivial thing. Now, in order to understand why the theorem is true, the proof that is given here is again a typical Rao Bhim way of proving things, which does not give you any intuition. Now, what it says is the following: A transpose U or B transpose U. So, whenever I give you any two vectors, say V and U, and I form this, what is this? Does this mean? It says VI UI. What we typically call is the dot product of V and U. If this is equal to 0, that means they are mutually perpendicular. Now, this perpendicular or orthogonality is something that they have taken up in a later chapter. So, if you really want to do this theorem, that should come in that chapter. But Rao Bhim Shankaram being Rao Bhim Shankaram, they have put it here with a very weird kind of argument. So, the actual argument is this, that suppose I take some particular subspace. So, let us just understand it pictorially. I have some particular subspace and then whatever vector I hear in this subspace, say I take any vector V here, whatever vector I take, so this is the origin, whatever vector I take, I find that U is a wonderful vector such that it is orthogonal to V. So, what does that mean? That U must be something like this, right? It must be perpendicular to the entire plane. So, if I have this condition that for all V in this subspace, say call this subspace S, I have this condition V prime U is equal to 0. That basically means that U must be perpendicular to the entire surface, entire plane. So, when I say A prime U equal to 0, I am basically saying that whatever column of A I take, that is orthogonal to U. Because what is A prime? A prime is nothing but A lying horizontally. So, here are the columns of A, now they are lying horizontally. These times U. So, this means this times this plus this, this times this, that is the first entry. Then this times this, that is the second entry, which is also this. So, this times this. So, the dot product of the first column of A with U is 0. The dot product of the second column of A with U is 0, and so on. That is, U is perpendicular or orthogonal to all the columns of A, which means U must be something which is orthogonal to column space of A. So, if this is column space of A, U is a vector which is perpendicular to that. And this means U is a vector which is perpendicular to B. Now it says whenever U is perpendicular to A, you have U is perpendicular to B. What does that mean? That basically means B must be itself something which lies in the column space of A. And that is precisely the condition. If B is in the column space of A, then obviously whenever U is perpendicular to column space of A, it must be perpendicular to B as well. And conversely, if B is not in the column space of A, say, so I am trying to prove the other way around. Suppose this holds, say, I am going to show that then it is consistent. So, is it possible that B is not in the column space of A and it still holds? Well, that is not possible, because suppose B is something like this, then all that you do is you take U to be precisely the component of B which is perpendicular to column space of A. Because B is not in column space of A, there must be something which is the part of it which is outside column space of A. That and this is not 90 degree obviously. So, you will get a U which will not satisfy this condition. Now, the proof that I gave is kind of a geometric proof to give the basic intuition. The proof that they have given just an algebraic thing, but whatever I have given can be made perfectly precise. But I will not go further into this, because as I said, this theorem is not going to help you in either solving problems or thinking about the thing in an intuitive way. The next theorem is a very important theorem. Theorem 5.3.3, it says if you have a consistent system, so it has got at least one solution, pick any one solution, any particular solution, then the general solution will be given as U plus null space of A. Very important result. Now the proof is super trivial. It's more like a definition of null space than anything. So I have to show that two sets are same. So if you take any solution, it must be of this form. If you take anything here, it must be a general, it must be a solution. So I will first show this to this. So let V be anything in the left hand side. So by this I mean let V be any particular solution. I want to show that V must be of the form U plus some element in null space of A. By the way, by this I understand that this is a set. When I add a vector with a set, I mean with each element of this set I add this vector and consider the set of all such sums. So in order to show that V is in this, enough to show that V minus U belongs to null space of A. So I want to show this. I put a question mark. And what does that mean? This means if I multiply this by A, I should get 0. So let's see whether I am getting it. AV minus U, that is AV minus AU. Because it's a solution, this must be equal to B. Because that is also a solution, that also must be equal to B. So I get 0. And hence I can indeed see that V minus A is in null space of A. Next I have to prove the converse. If I take anything here that is in the general solution, so now I will say let W be in U plus null space of A, which means that is W equal to U plus some vector, call it Z, where Z is in null space of A. I want to show that this is a solution. To show that this W must be in the set of general solutions. This is to show, and by this I mean I have to show AW is equal to B. Well, let's do it. It is AU plus Z, that is AU plus AZ. This is already B, and this by my very property of Z is in null space of A. So this is 0, so this is equal to B as required. As I said, this theorem is of great importance, unlike theorem 5.3.2, which is just useless rubbish. After this, the book goes on in a somewhat rhetoric mode and says that for any system Ax equal to B, we define the corresponding homogeneous part of that system as Ax equal to 0. So just replace B by 0. Now any solution to this is basically an element of null space of A. So we can say general solution of this system is any particular solution of the system plus general solution of the homogeneous part, because general solution of the homogeneous part is precisely null space of A. Again, this is just a fancy way of restating the last theorem. To prepare ourselves for the next theorem, which is very important, we have to remind ourselves of the following fact about vectors. Suppose I give you a bunch of vectors and another vector, and I ask you the question, is V a linear combination of these things? And the answer is, again, it is a little more than just change of language, is yes, if and only if V belongs to the span of the UIs. As I said, it is a little more than just using a different language. That is precisely span, set of all linear combinations. Now if I further ask you the question whether the linear combination, suppose it exists, is unique, in that case it will be, you need this condition of course for its very existence, and for the uniqueness you will need UIs linearly independent. So clearly understand why linear independence gives rise to that uniqueness. It is because if you have non-unique setup, suppose you have got two different linear combinations, you have both AI UI as well as BI UI, both these things are equal to V. You subtract one from the other and you will get AI minus BI UI, that will be equal to 0. Because these are linearly independent, all these things are forced to be 0, that is all the AIs must be same as BIs, so two distinct linear combinations cannot exist. On the other hand, if you see that some distinct linear combination exists, then of course UIs cannot be linearly independent, so they are actually equivalent. And if they are not linearly independent, you can always create some way of expressing V in two distinct linear combinations of the UIs. We are going to use this fact in the next theorem. The next theorem is a consistent system Ax equal to B has unique solution if and only if A is full column rank. So I already tell you that it is a consistent system, so B belongs to column space of A. It is already a linear combination of the columns of A, and it will be unique obviously if all the columns of A are linearly independent. That's precisely what I discussed. And columns of A are linearly independent, that is what is called full column rank. That's it. I have taken the liberty of recasting the next theorem in a more obvious and intelligible way, and then I will discuss their way of writing it. So I have a system Ax equal to B. I am merely summarizing whatever we have already seen. It has no solution if B does not belong to column space of A. It has unique solution if B belongs to column space of A and A is full column rank. It has non-unique solution, that is at least two distinct solutions, if B is in column space of A and A is not full column rank. Now, Rao Bhim being Rao Bhim, they will not state things easily, so they have stated the same thing but in an unnecessarily complicated way, which I am going to tell you now. For the first condition, they are writing it as rank of A appended B, that is greater than rank of A, which is just saying B does not belong to column space of A. When you add this additional vector, in that case the dimension increases. So instead of writing this, they are writing this more complicated looking thing. For the second condition, they are first saying that A has got n columns and then B belongs to column space of A, that is rank of AB is same as rank of A. So appending one other extra column has not increased the dimension, and A is full column rank. That condition is precisely this, that all the columns are linearly independent, which means the dimension of the column space of A exactly equals the number of columns. So this condition says B is in column space of A, and this condition says that A is full column rank. And the last thing is similarly, I have still this condition still, B being in column space of A, that is governed by this equality, and A is not full column rank, which means there is some linear dependence among its columns. So the dimension of the column space must be less than the number of columns, because some of the columns are not bringing any fresh contribution. So this says A is not full column rank. But remember the black part, and once you remember the black part, you understand it is nothing more than whatever has already been stated and just is common sense. To understand the next theorem, which is yet another Rao Bhim rubbish, it will help to take a look at this example. Suppose I ask you to find a general solution of this, you will immediately notice that the second two equations are not important at all, the second and third equations, because they are nothing but multiples of the first equation. Multiply this with 2, you will get this. Multiply this with 3, you will get this. So you can focus your attention only on this. And here you notice that there are three unknowns but only one equation. Now the coefficient of x1 is non-zero. So immediately you can take everything else on the right hand side and just write x1 equal to 1 over 10 minus 5, I should write the 6 what? 6 minus 5x2 plus 6x3. So whatever arbitrary values of x2 and x3 you take, if you define x1 like this, then it is going to satisfy the first equation, and as a result it is also going to satisfy the other equations. So we had a system like this with the property that only the first row actually mattered, because all the other rows were multiple of the first row. So I could focus my attention on this, and even in that first row, so the equation was this times this equal to only the first element here, and even there I had the advantage of this being a non-zero entry. As a result, I found that I could set all these variables in an arbitrary way and just work out this variable in terms of the other things by taking its reciprocal, and that gave me the general solution. Now the theorem that is going to follow will just generalize this in the following trivial way. It is not that I will be saying everything is a multiple of only the first thing, but I will allow a little bit more things. So maybe the first few rows are the only thing that matters, and the rest are just linear combinations of those things, which basically means that out of all the rows, only the first few are linearly independent. Now I must make sure that it is not just enough that these things are multiples of that, but the corresponding things here must also be multiples, because otherwise the system will not remain consistent. Like if I have x plus y equal to 5, and the next thing is 2x plus 2y, this is multiple of that, but I need this to be also the corresponding multiple, otherwise it will not remain consistent. So if that is the case, I can basically ignore all the remaining equations. Just as here I can ignore this equation, and I also assume that this part, suppose there are many such things, these are many things, that is a non-singular matrix. If that is the case, I can solve the entire system. So I have given you some labeling. So I consider this A11 part, which is non-singular, invertible. A11 is non-singular, and R is the rank of the entire matrix in this case. And I say that this part, that is A2B2, this part brings no fresh contribution, so this part is just belongs to the span of the top part. So I can write it in this way, that row space of this is inside row space of A1, B1. And there are various ways of writing it. You might say that rank of this is R, so since the rank is already R, there cannot be any fresh contribution here. So here R is rank of A colon B. So these are all equivalent ways of saying that this lower part brings no fresh contribution. I can write it in this way, I can write it in this way. Okay, so the system of equation now reduces to only the top part, and that top part is this A11 x1. Remember, that's also a vector, all the unknowns here, and x2 is all the unknown here, plus A1 to x2 is equal to b1. Now I have assumed A11 is non-singular. As a result, I can do the same trick that I showed earlier. I can just write x1 equal to A11 inverse b1 minus A12 x2. I take this on this side and pre-multiply by its inverse. So what do I get? I can take any arbitrary values for x2, I do not mind, form this expression, put that as your x1, then it is guaranteed that the first R equations will be satisfied, and if the first R equations are satisfied, then immediately all the equations must be satisfied. That was theorem 5.3.6 from the book, which I do not state here because that theorem is given as a beat paragraph. I do not have enough space to write it.